Okay, good morning all. First, I need to share my screen. Okay, is my screen visible? Is my screen visible? Okay, so today's topic for discussion is Boolean algebra. Mm, check your syllabus first, I think. Just a minute, no? I need to check your syllabus. Okay, so from first unit, I think analog and digital system is covered. Then representation of signed number is covered. Then two's complement, arithmetic, BCD addition, subtraction, octal and hexadecimal addition, subtraction, derived gates. I think all are actually covered in last three lectures. Now, next point from your syllabus is reduction of Boolean expression. But before that, you must understand what is there in Boolean algebra, right? Since you need to reduce Boolean expressions for digital simplification or digital circuit simplification, you may say. So, to reduce the Boolean expression, you first must understand what actually Boolean algebra is. Now, see, this Boolean algebra is based on mathematical logic, right? So, this Boolean algebra is based on mathematical logic, and uh, you again say that this is a branch of mathematical algebra as well, right? So it is a kind of a branch for algebra, but this is different. Since it is branch of algebra, it is well known for algebraic expression and all. But what is important here in this Boolean algebra is expressions are denoted based on true and false values. Since those trues and false values are logical, so in terms of you can say solve those expressions, no, you may actually work on few binary operators, few unary operators with those values, right? So it is a branch of algebra. You can say again it is based on logical values, right? True and false, right? So it is based on logical values, and that is simply called two values are simply called true and false, right? True is denoted as 1 and false is denoted as 0, right? Uh, just like you learn mathematical algebra in first year, this Boolean algebra has also some certain rules over there, and it is basically differ with your you can say traditional algebra or ordinary algebra, right? So this is even the branch of algebra. It is differ in terms of a few things there in ordinary algebra, right? And even you learn, I think, binary number system. Since you see something there, just like binary algebra, sorry, binary number system and Boolean algebra, but there is also a difference in between this binary number system and ordinary number system with this Boolean algebra, right? So we'll see some basic terminologies differences in this, and then we'll go for rules and all, right? So first thing is there, I say that this is difference, differ than your ordinary algebra. So the difference in between Boolean algebra and ordinary algebra is like, if you have a plus a, if you talk about ordinary algebra, no, it is possibly 2a, right? It is possibly the answer is 2a. But in Boolean algebra, no, a plus a is a, right? Why is it so? Since Boolean algebra is based on logical value true and false, that means true or true is true. Getting? So this is how this normal, you can say Boolean algebra is differ in with normal algebra. In this as well, a dot a, you may say that this is a, right? Why it is a? You consider any value of a, it is your output. If you consider a is 0, then 0.0 is 0. If you consider 1 for a, then 1.1 is, sorry, 1, right? So this is how this, you can say, Boolean algebra is differ in terms of those logical values with normal algebra, right? Also, it has few logic operation. One is or operation is there, right? So those are some basic operation. Then and operation is there. One more operation is not operation. So those are few operations, basic operations are there in, you may say, in Boolean algebra, right? So those are few basic operations in Boolean algebra. Few operations are called derived operations in terms of Boolean algebra, and those basic derived operations are NAND, NOR, then XOR, XNOR. So those are few derived operations which are present in Boolean algebra, right? So this is, few basics, or you may say it is a kind of introduction for Boolean algebra, right? So in this, all I think covered earlier. Few things are remaining. XNOR expression. So XOR and XNOR expressions are remaining. So we'll see a detailed, what do we say, detailed explanation on this latter, but time being, what actually expressions are present there, we'll see. So A XOR B is A B complement plus A complement B, right? How actually they write this expression, we'll see later, but time being, keep in mind that this is the expression for XOR, and for XNOR, A plus B plus A complement B complement. as and when we start with few Boolean expression, you will understand how actually those expressions comes out, right? But time being, just keep in mind that this is the kind of expressions we have for XOR and XNOR there in algebra, right? So this is a basic introduction for Boolean algebra. Till now it is clear. Till now it is clear. Have you got the points? Hmm? Okay, okay, okay. So first and foremost thing is, there should be certain laws for any rather algebraic system. So just like ordinary algebra, in Boolean algebra we have a few laws and axioms, right? So we'll see uh, few axioms and laws for Boolean algebra. Now, what is axiom? What does it mean? Hmm? Anyone knows about axiom? Pronunciation may be differ. तुम्हाला याच्यात मॅथ्सला वगैरे वेगळं प्रोनाउन्सिएशन पॉसिबली सांगितलं असेल. प्रोनाउन्सिएशन डझंट मॅटर. एक्झाम्स माहिती आहेत का तुम्हाला काही? असं काही सांगितलंय का मॅथ्सला वगैरे किंवा डिजिटल सिस्टीमला? ओके. So axioms, no, this is a state of expressions, right? There are a few expressions that you need to accept without proof, right? Those are expressions. Axioms are expressions that you need to accept those expressions without proof. And further algebra is based on those axioms, right? So it is set of expressions wherein you are not asking for any proof for those axioms. And if you have those axioms, then you may go for different laws based on those axioms, right? So just write a definition for axiom, right? Axiom of Boolean algebra. I'll give you a definition for axiom. Just note it down. Axiom of Boolean algebra are a set of logical expressions. Axioms of Boolean algebra are set of logical expressions that we accept without proof. That we accept without proof. That we accept without proof. And upon which and upon which we build a set of useful theorems, and upon which we build a set of rules, right? So there are few basic operations that we discussed earlier in Boolean algebra, and those operations are and operation, or operation, and not operation. So axioms are based on those axioms are based on those basic operations, right? So axiom 1 is 0 into 0 is 0. And keep in mind that those are logical values, right? Keep in mind that those are logical values, right? Then second is 0 dot 1 is 1. 1 dot 0 is 1. 1 dot 1 is 1. So this is about AND operation. Then for OR, 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1, 1 plus 1 is 1, right? So this is for OR, and for NOT, one complement or one bar is equal to 0, and 0 complement or 0 bar is equal to 1. So um, those are few you may say axioms for this thing, Boolean algebra, right? So on those axioms, laws are based, right? On those axioms, laws are based. So we'll start with few laws now, right? So first is complementation law. First law is complementation law. Now, what does that mean? Complement means, hmm? Yes, complement means anyone. Complement means put it in chat now. Are you with me? Are you with me? Complement means yes, yes. Okay. Remaining things except that number. Okay. So keep in mind that complement is inversion, right? Complement is inversion. So whatever you have, you just actually invert the things in complement, right? So first law states that zero's complement is equal to 1, right? And second law says that one complement equal to 0. Third law states that if A is 0, then its complement, that means A complement is always 1. And if A is 1, then its complement is always 0. So those are four laws about complement, right? Complementation. So it is simply an inversion. 0 complement is 1, 1 complement is 0. If A is 0, then its complement possibly be a different value, that is 1, right? If you have only 0 or either 0 or 1, right? One more law which is there in complementation is if you have double complement, right? If you have double complement, then you will get the original value, right? If you have the double complement, that means A's complement is 0. Then if A is 1, then A's complement is 0. Again, A's complement is 1, right? A complement's complement is 1. That means it comes the original value. So A double complement is always the same value, right? So this is about, a complement laws. Then next is AND law. Oh, sorry, AND laws. If A law first is A and 0, what could be the value? What could be the value? 0. Why it is 0? If we have two values, that is 1 and 0. If we consider 0 dot 0 is 0 and 1 dot 0 is also 0, right? Then this law is called null law, right? This law is called null law. Then next is a dot 1 is a. Again, consider a's value. If a is 1, if a is 1, if a is 1, 1 dot 1 is 1, and if a is 0, 0 dot 1 is 0. So, for this law, result is depends on a's variable, rather a's value, right? So, whatever value of a is there, it will there, right? So this is referred as identity law in terms of Boolean algebra. Then third is a dot a is a. Fourth is a dot a complement is 0. Since if you consider this value is 0, it is obviously a 0. If you consider this value as 1, then complement possibility is 0. So 1 dot 0 is again 0. So the value is 0, right? So this is about, and laws. And next is or law. Or law, from that first is a plus 0 is equal to a. Second, a plus 1, right? A plus 1 is 1. This is called identity in terms of OR law, and this is called null law in terms of OR, right? So a plus 0 is a means the value, the result is depends on a's value, whereas in second law, the result is based on 1. Why? If suppose this value is true or false, uh, true or false, it doesn't affect on result. Why? Because it is ORing operation and one value is true. If one value is true, that means result it depends on that only. So it is 1 there in OR law, right? Second is a plus a is a, and a plus a complement is 1, right? Why it is so? 1. Okay. Since if you consider this value is 0, then its complement is 1. If you consider this value is 1, complement is 0. So in those expressions, so any value at given point of time is true. For that reason, our result is 1. So what I feel, even though in your book this is given, sorry, even though in your book this is given as identity rule, what I feel is this possibly be identity rule for OR, right? But in your book, it is given as this is your identity law, right? So keep in mind that and check the facts later after this lecture, right? So this is about OR law. So those laws are for basic operations. Now, few things are there about different laws. Now, commutative law, right? Commutative law. What actually this law refers for? So this law is refers for change in position, right? Change in position of variable for those operations, right? So first law states that A plus B is equal to B plus A. So change in position is possible in Boolean algebra, right? So if you consider the operation in that case variable, you allow that gate given as A as first input or B as first input anytime, right? So this says that A plus B is always equal to B plus A, right? This is same happened with another basic operation, that is A dot B equal to B dot A. So you can change the input position uh, anytime in Boolean algebra, since those values are the result for change in position are same both the time, right? You can check those things with truth table as well, right? How to give a proof for those law? Just write down the truth table for this. If I consider truth table for this, then you what you need to write is A, B, and the combination. Since there are two variables, how many combinations, possible combinations are there? Four, right? What two values? 0 and 1. So possible combinations are four. That is 0, 0, 0, 1, 1, 0, 1, 1, right? Those are possible value. What you need to check is you need to find A plus B and B plus A. So in first column, you need to identify A plus B's values, and then you need to identify B plus A. The values of both those columns should be same, right? If those values are same, then hence it is proved that this law is correct, right? So you can do this style of, you can say, proof for this expression as well, right? How and where I need to write a result, that I'll show you next expression. Since it is easy, I'm not giving a detailed explanation on those proofs. You just write down those truth table in your notebook after completion of this lecture, and then so proof is given in this way, right? Next is associative law. Okay. Now next is associative law. So law first is A plus B plus C is equal to A plus B plus C. So this is how association works. So you can what you say, or any gate with any, and then add the result of that OR gate into a different gate, right? So this could be possible in case of Boolean algebra. This is given by associative law, right? Second law is A dot B dot C equal to A dot B dot C, right? So this is also associative law. I'll show you a difference in between. See, this is, expression. A is here, B is here. Result comes out from this combination. you can give that result to another operation, and is your result, right? In another case, you can have two input like B and C. If you get out result from this, and if you pass to the second and get with A, or if you ANDed that result with A, the result of this circuit and this circuit should be same, which is given by this associative law. Again, you try the proof by using truth table method as well, wherein what you need to do is you need to write A, B, C. Since there are total three variables, that means how many combinations are possible? 2 raised to 3 is how many combinations are possible? 2 raised to 3 is 8. Yes, 8 combinations are possible of three variables. That means 0, 0, 0 to 0, 0, 1 up to 1, 1, 1. Total 0 to 7 combinations are present. Then you need to write A dot B, then you need to write A B dot C. Then you are combining A dot B's column with C, and then A's, uh, then B dot C's column with A, right? And those columns should be the values from truth table of column A dot B dot C and A dot B dot C should be same, right? So this is how you can give a proof to this associative law. Okay. Till now, anyone has any problem with Boolean algebra? Till now, anyone has any problem? Have you understood the things that is given related to laws? You have to keep in mind all the things while reducing the expression. So those laws we are actually using in reducing Boolean expression. So I'll give you a aim, right? Why actually we are reducing a Boolean expression? The reason behind is if we reduce that expression, the reduced expression gives you result same as that of original expression. But if you reduce that expression, that means the circuit which is based on that expression could be given, or based on that reduced expression is given the same result as original digital circuit. So we actually trying to reduce the digital circuits, right? Whatever we are trying to build, no, in that digital circuit, those circuits are in reduced form. So for that reason only, we are looking for the reduction of Boolean expression, right? So this is about associative law. Now I'll give you next law is distributive law, right? In that case, law first is A of B plus C is equal to AB plus AC, right? You can solve this thing by using direct expression that keep LHS with you. A into B plus C, directly multiply the things. A into B plus A into C, which is exactly equal to RHS. If you take RHS for simplification, then AB plus AC Now, what is common? A is common in expression. Take that A out, then B plus C is your expression, which is again same as your LHS, right? This is how also you can uh, give a proof for this law. Again, one more method is just like your traditional ABC, total three variables, eight combinations. Then you need to find B plus C. Then you need to find A into B plus C. Then you need to find AB. Then you need to find AB. Then you need to find AC. Then AB plus AC, right? And the column from this and sorry, the value from this column and value from this column should be same. So I'll give you the instruction that just try this, right? Just try this. Try out the truth table. Just write down a truth table for this. I'll give you the inputs 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. So those are three values. Just find out ORing of B plus C, then A into B plus C, AB, AC, and A plus B. I'll give you 3 minutes. In next 3 minutes, you have to complete all those columns and addition. Your time starts now. Okay. Your time is over. You completed this. Okay. Okay. Is it the same column or it'll give some different thing? Okay. Okay. No issues. So We'll take a second law in distribution, and that law is A plus BC is equal to A plus B and A plus C. Right. So this is what we say second law for distribution. Right. So what is there in distributive law? If we add the two variable and odd with another one, the result is same as ORing of same variable with two different variable from that expression and ANDing the result of both the expression. So this law states the same thing here. So since RHS is what we say huge in this expression, we need to take RHS to solve, right? So what is there? A plus B and A plus C, right? So what we need to do here is we are actually solving the things there. So how we are going to solve here in this expression is we need to take one variable and check the sign. So here multiplication or dot is there. So we need to multiply this variable with both the variables and we are splitting on this plus sign and ne next is second variable again with the variable, right? So the expression should be like a into a plus a into c, right? This plus sign comes here. Now a plus a into a plus c. Now this plus sign. Now b into a plus b into c, right? This plus sign comes here, right? So this is how we actually multiply the things. Now we'll rewrite the expression in correct form. Now what we need to check here is we need to check a common thing, right? What is common there in expression is A is common in three terms, right? If A is common in three terms, that we need to write there, right? So A is common. If A is common, that means one only remains there since A is common out of this expression, then C, then B, right? So this is about all three expressions, then B, C. If we remember that axioms therein, your Boolean algebra, if we odd anything with 1, the value is true always. It doesn't consider the values of other variable in that case. That means this is the expression value for this is true always, that is 1, right? So A into 1 plus BC, right? So A into 1 is BC. That means anything into 1 is that value only. And that is equal to A. So A plus BC. So here comes your LHS, right? So this is there in distributive law, right? So this is about the distributive law. You can explain or you can give proof for distributive law like this, or the way which is there, like we see earlier by using expressions and you can say a sign, right? Or sorry, not sign, by using gates, right? You can use basic gates as well. So this is about distributive laws. There are two distributive laws. Okay, so we'll see next rule is redundant literal rule, RLR, redundant literal rule, right? From that, law 1. What law 1 states that if we have the variable and we are if we have variable if we or that variable with ANDing result of complement of same variable with another variable, then it comes as A plus B. That means whatever there is in complement part should be removed, right? So how we are going to check the proof for this is, if suppose this is my A, so need to complement this A for A complement, and then B need to pass to AND gate. Here it is a result of A complement B that we need to OR with A, right? So this result is same as OR gate. This result is same as OR gate, right? You can check this with truth table, right? You can give proof for this is truth table, right? You can try out with a different method as well. This is expression. We'll take LHS for solving A plus A complement B. Now what we need to do here is we are trying to split this on multiplication. So A plus A complement and A into A plus B, right? So here it is the expression A plus A complement and A plus B. So if we take an OR result, any variable with its complement, the result is always 1. Why is it so? Because anything is there, its complement is there. If 1 is in expression, its complement is 0, but 1 is there in expression. If 0 is there, its complement is 1. So 1 is always there in expression, right? If 1 is present in expression, that means that expression is true always. It does not depend on another variable, right? So this 1 is there, 1 into A plus B. In case of ANDing, again, the value is depend on this variable and not on 1. Why? 1 dot 1 in multiply by anything is that anything value, right? So that is something called A plus B. And this is how the result comes. This is your RHS, right? So this is your redundant literal rule 1, and law 2nd states that A into A complement plus B is equal to AB. This is law 2nd. Okay, try to solve this. Keep LHS here as it is for solving. Okay, just try to solve this. I'll give you 2 minutes. Try to solve this. So, 1 is 0. Okay, yes, yes. Okay, done with the expression. Done with the expression. Okay, we'll see the next two laws, and that law is called idempotence law. Now, what is idempotence law is? Idempotence means same value, right? Idempotence means same value, right? So, if you consider in law first, A dot A is A always, and A plus A is A always. This is how the same value treated. Now we'll check the expression with values. If it is 0, then 0 dot 0 is 0. That means whatever we consider A, the output is A there. Again, we consider 1, 1 dot 1 is equal to 1 here, right? In case of next, if we consider 0, then 0 plus 0 is 0. If we consider 1 for A, 1 plus 1 is 1, right? So this is how you give a proof for idempotence, right? Idempotence means same value. So we complete, I think, today total 8 laws from Boolean algebra. Total 8 laws we are completing. Total, I feel 13, 14 laws are there. From that, we check total 8 laws, right? Remaining we'll see in next lecture.